Scientists have found 3 new examples of a very exotic form of matter made of quarks. They can yield insights into the early universe. Scientists working at the CERN laboratory recently announced the discovery of exotic matter not seen in nature, 2 different Tetra Quarks and a pentaquark. All of which were created inside collisions between pairs of protons slamming together at speeds very close to the speed of light. The energy of these collisions is literally transmuted into these exotic particles, a process governed by Einstein's famous equation E=mc². They will provide a new method for studying the force that binds the centers of atoms together. What are quarks? Quarks were proposed in 1964 by American physicist Murray Gell-Mann as a solution to a big problem at the time. From the late 1940s through the early 1960s, physicists had discovered hundreds of particles with a dizzying array of masses, electrical charges, lifetimes, and ways in which the particles interact. So many different particles had been discovered with such a diverse range of properties that researchers at the time called the menagerie the particle zoo. At the time of their discovery, these particles were the smallest objects known. Gell-Mann broke through the confusion when he realized that the zoo particles weren't the smallest objects in nature. Rather, the inhabitants of the subatomic zoo were made of even smaller particles, the quarks. Gell-Mann's original idea was that 3 types of quarks existed, which he called the up quark, the down quark, and the strange quark. The heaviest particles known at the time were combinations of 3 quarks. For example, the familiar proton consists of 2 up quarks and 1 down quark, while the neutron consists of 1 up and 2 downs. The name for these heavy particles is baryons. From the Greek word barous, heavy. The middling mass particles are called mesons, from mesos, middle. Mesons consist of a quark and an antimatter quark. The most common meson is called a pi meson, pion. And one particular pion consists of an up quark and a down antimatter quark. The lightest particles, called leptons, drawn from the Greek leptos, light, are a different class of particles entirely and contain no quarks. The most famous is the electron. While quark theory explained much of the known particle zoo, it also predicted the existence of particles that hadn't yet been observed when the theory was proposed, for example, the omega baryon, consisting of 3 strange quarks. However, the theory was validated a few months later, when the omega baryon was discovered. Quarks are part of the standard model of particle physics, which is universally accepted within the scientific community. While Gell-Mann originally proposed that only 3 quarks existed, scientists have now discovered a total of 6. Their names are up, down, charm, strange, top, and bottom. In the past half-century, researchers have discovered most of the possible ways that they can combine 3 at a time, or as a quark and antimatter quark pair. Not just trios, but quartets and quintets. However, in Gell-Mann's original paper, he did not limit the possible quark configurations to just the 3 quark baryons and the quark-antiquark pair mesons. He also postulated a 4-component Tetra Quark, made of 2 quarks and 2 antiquarks, and a 5-component pentaquark, made of 4 quarks and an antiquark. Searches for these particles were unsuccessful for years, but in more recent times, candidate particles occasionally have been detected. In the last few years, an experiment at the CERN laboratory, called LHCb, has been trying to find previously unknown particles. Its recently announced discovery isn't of an entirely new class of matter, after all. A handful of tetraquarks and pentaquarks were known to exist, but rather of new variants. 2 of the particles are tetraquarks. One of them is composed of a charm quark, an up quark, a down antiquark, and a strange antiquark. The other is made up of a charm quark, a down quark, an up antiquark, and a strange antiquark. Note, antiquarks are denoted with a line over the letter. The other new particle is a pentaquark, made up of a charm quark and its antiquark in combination with an up, a down, and a strange quark. It is the first pentaquark found to contain a strange quark. The significance of exotic matter. So, what is the significance of discovering new examples of very exotic forms of matter? It allows us to better understand the nature of the strong nuclear force under extreme conditions. The strong nuclear force is responsible for, among other things, holding atomic nuclei together. It also has implications for our understanding of the evolution of the very early universe. Shortly after the Big Bang, the universe was so hot that quarks freely roamed around and were not captured inside bigger particles. approximately 1/millionth of a second after the Big Bang. The universe cooled enough that the strong nuclear force began to gather quarks inside the protons and neutrons that makes up the cosmos, but during the transition, it must have assembled tetraquarks and pentaquarks as well. While these primordial particles have long since decayed. A full accounting of the origins of the universe will require that tetraquarks and pentaquarks be understood.
That was it for now. For more content like this, subscribe to our channel.